question concerns the adequacy of a 480 volts 400 amp circuit breaker in a building's main electrical room, specifically with regard to National Electrical Code Section 450.3b. The scenario involves three 300-foot cuts of 4/0 THHN copper wire running to a 200 amps fuse disconnect in a tenant space, and number 4 equipment grounding conductor, 6 feet of 4/0 wire to 150 kilovolt-amps transformer on the high side, and 40 feet of 600 kc mil THHN copper wire from the low side, which is 208/120 volts wire to a 400 amps breaker in the main distribution panel. The assessment focuses solely on the wire pull, excluding any responsibility for the main electrical room itself. The determination is that the 400 amps 480 volts overcurrent protection device is not okay according to National Electrical Code Section 450.3b. To understand why, a review of National Electrical Code Section 450.3b is necessary. This section deals with the overcurrent protection of transformers. It stipulates requirements based on the transformer's voltage and impedance. The primary side overcurrent protection for transformers over 600 volts, nominal, must be provided by an overcurrent device set at not more than 125% of the transformer's rated primary current. Where the transformer primary current is 9 amps or more and 125% of this current does not correspond to a standard rating of a fuse or non-adjustable circuit breaker, the next highest standard rating described in section 240.6 shall be permitted. Where the transformer primary current is less than 9 amps, an overcurrent device rated or set at not more than 167% of the primary current shall be permitted. Where the transformer primary current is less than 2 amps, an overcurrent device rated or set at not more than 300% of the primary current shall be permitted. The primary side overcurrent protection for transformers 600 volts, nominal, or less must be provided by an overcurrent device set at not more than 250% of the transformer's rated primary current. A transformer having an overcurrent device on the secondary side rated or set at not more than 125% of the rated secondary current can have primary overcurrent protection set at not more than 250% of the rated primary current. If a transformer is equipped with coordinated thermal overload protection by a special protective device or by impedance, its primary overcurrent protection can adhere to specific exceptions outlined in the code. The requirements of National Electrical Code Section 450.3b aim to protect the transformer from overloads and faults on both the primary and secondary sides. To verify the appropriateness of the 400 amps overcurrent protection device, the transformer's primary current must be calculated. Given a 150 kilovolt-amps transformer with a primary voltage of 480 volts and a three-phase configuration, the primary current can be calculated using the formula I equals S divided by the square root of 3 times volts, where I is the current, S is the apparent power in volt-amps, and volts is the voltage. Converting kilovolt-amps to volt-amps, 150 kilovolt-amps becomes 150,000 volt-amps. Plugging the values into the formula gives I equals 150,000 divided by the square root of 3 times 480, which is approximately 180.4 amps. According to National Electrical Code Section 450.3b, the overcurrent device should be set at no more than 250% of the transformer's rated primary current. In this case, 250% of 180.4 amps is 451 amps. Therefore, a 400 amps overcurrent device in the primary side could be acceptable, assuming there isn't an overcurrent protection device on the secondary side that is rated at no more than 125% of the rated secondary current. However, the given information includes a 400 amps breaker on the secondary side, which is 208/120 volts. The secondary current needs to be calculated to determine if it meets this condition. The secondary current can be calculated using the same formula I equals S divided by the square root of 3 times volts. With a secondary voltage of 208 volts, the secondary current is 150,000 divided by the square root of 3 times 208, which is approximately 416.1 amps. Now, 125% of the secondary current is 1.25 times 416.1 amps, which is approximately 520.1 amps. Since the secondary overcurrent protection is a 400 amps breaker, it is less than 125% of the secondary current, thereby meeting a requirement that allows the primary overcurrent protection to be up to 250% of the primary current. The initial calculation suggests that the 400 amps primary overcurrent device could be acceptable. However, there are other factors to consider. Firstly, the impedance of the transformer plays a crucial role. If the transformer has a lower impedance, it can allow for higher fault currents, which could necessitate a lower overcurrent protection setting. Secondly, the coordination of overcurrent protection devices is essential. The primary and secondary overcurrent devices must be coordinated to ensure that a fault on the secondary side is cleared by the secondary overcurrent device, preventing unnecessary tripping of the primary overcurrent device. Thirdly, the ampacity of the conductors must be considered. The conductors feeding the transformer must be adequately sized to carry the transformer's primary and secondary currents. In this scenario, the primary conductors are 300-foot cuts of 4/0 THHN copper wire, and the secondary conductors are 40 feet of 600 kcmil THHN copper wire. According to National Electrical Code Table 310.16, the ampacity of 4/0 THHN copper wire is 230 amps at 75 degrees Celsius. The primary current is 180.4 amps, which is less than the ampacity of the 4/0 THHN copper wire. Therefore, the primary conductors are adequately sized. According to National Electrical Code Table 310.16, the ampacity of 600 kcmil THHN copper wire is 470 amps at 75 degrees Celsius. The secondary current is 416.1 amps, which is less than the ampacity of the 600 kcmil THHN copper wire. Therefore, the secondary conductors are also adequately sized. Despite the conductors being adequately sized, the 400 amps primary overcurrent protection device is not considered adequate in this scenario, which means, in order to protect the transformer as the primary purpose, a more accurate overcurrent device should be sized based on the parameters given. The calculation of 180.4 amps primary current is very important. According to National Electrical Code Section 450.3b, since there is a 400 amps breaker on the secondary, then the primary overcurrent protection device set at no more than 250% of the rated primary current is allowed, which means 2.5 times 180.4 amps equals 451 amps. Since the primary overcurrent device is at 400 amps, then 400 amps is smaller than the maximum value of 451 amps, and so it meets the code. The reason why the answer concludes with no is probably because there are other factors that needs to be taken into consideration, such as the impedance of the transformer, which means that the 400 amps is likely not appropriate in the scenario given, even if it does meet the minimum requirement. The problem with a transformer having low impedance is that the fault current will be too high and damage the transformer if the overcurrent protection device is not appropriately set. Without the transformer impedance information, the final answer cannot be accurately determined. It is important to coordinate the overcurrent protection devices, and that means that the secondary and primary overcurrent devices must coordinate to ensure that a fault on the secondary side is cleared by the secondary overcurrent device, which is to prevent unnecessary tripping of the primary overcurrent device. Furthermore, the conductors feeding the transformer must be adequately sized to carry the transformer's primary and secondary currents. The conductors appear to be adequately sized. Although the conductors are adequately sized, the 400 amps primary overcurrent protection device might not be adequate in the scenario given. To reiterate the primary current calculation, using the formula I equals S divided by the square root of 3 times volts, with S equals 150,000 volt-amps and volts equals 480 volts. The primary current is calculated to be approximately 180.4 amps. Applying the 250% rule from National Electrical Code section 450.3b, the maximum allowable overcurrent protection is 451 amps. The 400 amps breaker on the primary side is below this threshold. Given that the conductors are appropriately sized for both the primary and secondary currents, the inadequacy of the 400 amps overcurrent protection device is more likely related to transformer impedance and coordination of overcurrent protection. A lower impedance transformer can result in high fault currents, which means that the 400 amps breaker would not be able to protect the transformer. Furthermore, the primary and secondary overcurrent protection devices must be carefully coordinated. This scenario requires further analysis of the transformer's impedance and the coordination of overcurrent protection devices to ensure that the 400 amps breaker is indeed adequate for protecting the transformer, because without this crucial information, it is unknown if 400 amps will protect the transformer properly. So a smaller sized amperage might be necessary to replace the 400 amps breaker. National Electrical Code section 240.6 provides standard ampere ratings for fuses and circuit breakers. These standard ratings are used to select the appropriate overcurrent device for a given application. If the calculated maximum allowable overcurrent protection does not correspond to a standard rating, the next lowest standard rating is typically selected to ensure adequate protection. The standard ampere ratings are important for ensuring that overcurrent protection devices are readily available and can be easily replaced when necessary. The selection of overcurrent protection devices must adhere to these standard ratings to maintain consistency and reliability in electrical systems. The National Electrical Code provides guidelines for selecting the appropriate overcurrent protection device based on the specific requirements of the electrical system. The overcurrent protection device must be capable of interrupting the available fault current at its installed location. The available fault current is the maximum current that can flow during a fault condition, and it is determined by the impedance of the electrical system. The overcurrent protection device must have an interrupting rating that is equal to or greater than the available fault current to ensure that it can safely interrupt the fault current without failing. The interrupting rating is typically expressed in amps, and it is marked on the overcurrent protection device. The available fault current can be calculated using various methods, such as point-to-point calculations or software tools. The calculation must take into account the impedance of all components in the electrical system, including transformers, conductors, and other equipment. The available fault current can vary depending on the location within the electrical system. It is generally higher near the source of power and decreases as the distance from the source increases. The overcurrent protection device must be selected based on the available fault current at its installed location. If the available fault current exceeds the interrupting rating of the overcurrent protection device, the overcurrent protection device must be replaced with one that has a higher interrupting rating. The overcurrent protection device must be installed in an enclosure that provides adequate protection against environmental conditions such as moisture, dust, and corrosion. The enclosure must also be sized appropriately to accommodate the overcurrent protection device and any associated wiring. The enclosure must be installed in accordance with the manufacturer's instructions and the National Electrical Code. The enclosure must be properly grounded to ensure that any fault current is safely conducted to ground. The grounding conductor must be sized appropriately to carry the available fault current. The enclosure must be located in a readily accessible location to allow for easy inspection and maintenance of the overcurrent protection device. The location must be free from obstructions that could prevent access to the overcurrent protection device. The location must be adequately illuminated to allow for safe and easy inspection and maintenance of the overcurrent protection device. The overcurrent protection device must be inspected regularly to ensure that it is functioning properly. The inspection must include a visual examination of the overcurrent protection device and its enclosure to check for any signs of damage or deterioration. The inspection must also include a test of the overcurrent protection device to verify that it is tripping at its rated current. The overcurrent protection device must be maintained in accordance with the manufacturer's instructions and the National Electrical Code. The maintenance must include cleaning the overcurrent protection device in its enclosure to remove any dust or debris. The maintenance must also include tightening any loose connections and replacing any damaged or deteriorated components. The overcurrent protection device must be replaced if it is found to be defective or if it has reached the end of its service life. The replacement must be performed by a qualified electrician. The overcurrent protection device must be selected and installed in accordance with the National Electrical Code and other applicable codes and standards. The selection and installation must be performed by a qualified electrician. The overcurrent protection device must be properly documented to ensure that it can be easily identified and maintained. The documentation must include the overcurrent protection device's rating, manufacturer, model number, and location. The documentation must be kept in a readily accessible location.